So after we create a partition, I think I alluded to it a second ago, we have to put a file system on it. To put a file system on it, we essentially use the mkfs command or some derivative of that command, which you'll see later on as I show you a demo or as you look at the screenshots we have for a demo. Anyway, different types available, NTFS, Windows, ext3, ext4, BTRFS, ButterFS, VFAT. There's many other file system types. For this class, we're not really going to get into the differences between them. I will have you on the assignment create one or two different types of file systems. But the Linux file system, the most common Linux file system, the one that Ubuntu uses currently is ext4. As part of that ext4 file system, we introduced this concept called inodes. First thing I would do is go watch this video that I have here in the link. Then come back and learn some more. But the file system is made up of inodes. An inode, my term, is a slot that contains metadata about a file. The inode contains the following. It'll contain the size of the file, the device ID like /dev SDA, the UID and GID, who owns the file, right? Pointer to the file location on the hard drive, so where it needs to go in order to find the file, and other information that's found when we use ls-l and or stat. So for example, if I on my, let's see, ls-l, that is accessing inode stuff like all this permission garbage and UID, GID, size, timestamps, that sort of thing. That's accessed when we're accessing inode data when I do that. Or if I do stat, whatever, some file, all this information is given to me down here. It's all, most of it's contained by the inode. So one important thing at the very bottom, the inode does not actually store the file name. So this stuff is not stored in the inode. Just the file name is not stored in the inode. Why do we care? So what? How, well, where is that stored? Well, the file name is actually stored in the directory itself. So Linux is just a collection of files and directories, or the file system, I should say, is a collection of files and directories. And so that name of the file is stored actually in the directory itself. So if we can do that, we've done the df command. Like df shows us how much space we've used up. You can see all my different partitions. I have a couple of them that are used at 100%. Now let's look at df minus I. And df just shows us our disk space. df minus I shows us how many inodes we've used. So you can see here I've used up 100% of my inodes, 78% of my inodes. Let's look at that one again. Dev SDA22. So notice that I haven't actually used all of the disk space on that, but I have used all of my inode space. What does that mean? Well, so each file is assigned an inode, but those files can be of various sizes. So it is possible to run out of disk space before you run out of inodes. Same as the inverse could also be true. It could also be possible to run out of inodes before you run out of disk space, as I just showed you. We cannot have more files than inodes. So let's say I have a file system with only 200 inodes. It's the maximum number of files I could have is 200. It's more common to use all the disk space, still have inodes left. So if we throw in our ls command, ls minus lai, we can see all of our files. We can see the inode number here in the left column that's attached to those files. So yay, each file is attached to an inode. The first, let's do, ls minus. The other thing, let's go back to, root. Let's go here. So each file is represented by an inode number. But as I look here on my root file system, let's look at the very top of my file system. If I cd to dot, where is it going to take me? It takes me the same place as dot dot at the root of my file system. So it's saying, take me to inode 2. Oh, but what if I cd into dev? Is that the same place? Or what if I cd into home? Is that the same place? No. What this means is all of these, so inode numbers have to be unique on a partition. If I move to another partition, they have to be unique. So this would signify dev has to be on another partition. Home has to be on a separate partition. Let's go check that out. So if I do df dot, my root file system's on SDA1. Let's go into home. df dot. That's in SDA3. So I can start reusing inode numbers again. Let's go into dev. df dot. This is a funny one. We don't care about it, but it is a different, it's kind of a runtime partition, I guess. And there's probably a more special word for that, but we don't really care. It is a different partition though. So inodes can be repeated. They have to be unique on a partition. So root generally has an inode of 2. If you find 2 file names on the same partition with the same inode number, then the files are not actually different files, but they are the same file with different names, such as a hard link. Once created, a hard link will always link to the file using the inode number, even if you rename, move, or delete the original file name. Symbolic links, however, get unique inode number and link to the name of the file, not the file itself. So if you change the original file name, the symbolic link is broken. Okay, so now I think we ought to look at some examples there of inodes. All right, so I'm going to create a file. It's cars.txt, ls-li cars.txt. We see that it was assigned an inode number of 39. Let's put some content in it. Toyota cars. And we can make sure it has that content in it. Great. The inode number shouldn't have changed, obviously. It's just still pointing to a particular location on disk. Let's do a symbolic link. Link to cars, whatever you want to call it. ls-li. So here's my cars.txt. It has an inode of 39. Link to cars. The link itself, this, has an inode of 44, but it really is saying go over to cars.txt. We've already learned that if I were to, it's just linked to the name. So if I remove it doesn't work. I mean, it's still there, right? Link to cars still, but link is broken because it's saying that it's just pointing to a file name. So a symbolic link points to a file name. Let's bring back our cars.txt. Cars.txt. Okay, so now I should be able to, symbolic link works. That work. I mean, so once again, the symbolic link, the file name here points to cars.txt. Let's try a hard link. And we also saw with a symbolic link, if I delete the file that we're pointing to, the content is gone. I can't get back to it. So let's make a hard link. So the hard link was made just same way, but without the -s. So I'll call this hard link to, let's do it the wrong way. Cars, hard link to cars, whatever. Okay, so now let's look what happened. Cars.txt, oops. Let's look at the inodes. Has an inode of 39. Hard link to cars, inode of 39. Okay, what does that mean? Well, remember before, when I deleted cars.txt, I lost the data because I couldn't get back to inode 39 anymore. Can you see that if I delete cars.txt now, I can still access the data through my hard link? So, whatever. I can, let's just, okay. So what I mean, they're linked. Basically, when I add data to either one of them, it's saying go to inode 39 and write my data blocks there where inode 39 is pointing to. If I were to delete cars.txt, I could still access the data because hard link to cars is still pointing to inode 39. One other thing I want to point out here. Let's look at this column. This third column of the ls command. I see a 2 there. I see a 1 here. Well, what does the 2 mean? The 2 means this is how many links in our file system table we have to that inode. So is that true? Yeah, cars.txt is pointing to 39, and hard link to cars is also pointing to 39. Let's try another one. Okay, so this will also point to cars, whatever you want to call it. Let's do this, and so now I have 3 links that are pointed to cars, which is interesting to look at a directory. So let's subdir. Let's look at this new directory I just created. Oh, by default, it says there's 2 links to inode 45. Let's see if we can find it. Well, here's one. This is just subdir. It's just an entry in my table that then points to inode 45. Let's go into subdir. So this dot is another entry that also points to inode 45. So let's say that inside of this, let's create a couple directories. So I've made it a couple different directories here. All right, why did I want to do that? Let's just look at this. Okay, so there's 12 links to inode 45. Wait. Inode 45. Wasn't that the one we were just doing? Where are those other 12? So I counted 2 a second ago. So we find them all? Well, here's one. I just created 10 directories. Let's go into D1. Oh, dot now refers to 45. So in each one of these directories, all 10 of them, there's now a new entry for dot that points to inode 45. So there's 10. Here's my 11th. And where was my 12th? Well, it was back here, right there. Subdir points to 45. So that's the 12th link to inode 45. So the only reason I want to bring that out is because maybe on a test I'll ask you something like this. All right. Or actually, let's go back here. So if you look at this line, if I give you this line, how many subdirectories will be in there then? Inside of subdir, how many directories will it contain? Well, it's got to contain at least 10. We've already counted the subdir, already counted the dot inside of that, and then there's 10 subdirectories that each have a dot in it. So that could be useful. So there's our little foray into inodes. We kind of looked at that, but there's some other, you can do that as well. We already looked at that. The other thing I would look about is if I move files around. So let's look at this. Let's see, du minus h. Well, I don't have anything that's huge. I was wondering if I had something that was larger than others. 40 meg. This 40 meg file. So if I say move this, whatever it is, into my subdir, boom. Why is it so fast? Because we're not moving inodes around. We're not moving blocks around. All we're doing is we're taking this entry in the table and putting it in a different entry. So it was a super fast operation. Now, if I were to move it, and once again, this isn't huge, so it might just be really quick. Let's also look at the mount, or df command will show what file systems are mounted. So I've got some over there on space D7. So I'm going to move my fat test. Oh, the other thing before I move it, fat test has an inode 37. Did not change, no matter where I move it on this partition. If I move it to another partition, it has to get a new inode number. So, I mean, theoretically, I guess it could be assigned the same one. But I'm going to move it over to space D7. Oh, I don't have permissions over there. Takes a little bit longer because it's on a different file system and because the system, I guess, is slow. But let's do ls minus lai on space D7. It was assigned a different inode number. So inode numbers only persist, I guess, if you're on the same partition. If you were to move a file to a different partition, the inode number changes. How about when we copy a file? Well, obviously when we copy a file, you got to go copy all the blocks. So that would also, we could try it here, whatever, let's copy cars to trucks.txt. And we see here cars has inode 39, trucks has inode 37. It has to have a new inode when we do a copy. So there's some other examples for you. We can find by inode number if we know the inode number. So one other thing to point out, where's the name of the file? Again, it's not in the inode, it's not in the data blocks, it's in the metadata of the directory. So the directory itself contains a table of the file names in the directory and the matching inodes. Think of it as a table, and the first two entries are always dot and dot dot, and the rest are all the directories and files within the current directory. So we already talked about when I move or rename a file within the same partition, we're not actually moving the data contents, we're just creating that new name or entry inside of a new directory. So even if it's a 10 gigabyte file, 100 gigabyte file, if it's on the same partition, a move is going to be super fast because we're just adding a new entry in the table. Now, copy, you're duplicating, so it would get its own inode number. Symbolic links, we already talked about that. And we already talked about symbolic links. And there's some examples you can go do at the end of these slides if you want. Yeah, we already talked about all that. So I think we're done with this one.